temperature also affects rate. If you change the temperature, you're going to change the rate constant. The way it works is scientists named Arrhenius investigated the relationship and found this, which is called the Arrhenius equation. T is your temperature in Kelvin. R is the gas constant in energy units, so we use the 8.314 joules per mole times Kelvin. A is the frequency factor, which is the rate that the reactant energy approaches the activation energy. And then E sub A is the activation energy, which is the extra energy needed to start the molecules reacting. Let's look at what that looks like. So for reactants and products for an exothermic reaction, we know that energy is given off, but the reaction doesn't happen instantaneously because of this activation energy barrier. So reactants need to be lined up correctly in order to form their products, and they have to, that activating process involves some energy. That's called the activation energy, or E sub A. Some reactions that are thermodynamically favored rarely happen because their activation energy barrier is so tall. So let's look at an example of what would have to happen for this reaction, the isomerization of methyl isonitrile. It will rearrange to acetonitrile. So basically we will weaken this bond here between the carbon and the nitrogen. The group will rotate and then a new bond will form. So for the reaction to occur, we need to break a carbon-nitrogen bond and form a new carbon-carbon bond. If you look at the energy profile, we have our reactant. Then up here at the height of the activation energy, there's the activated complex, or the transition state, where we've expended the energy to break this bond, but we haven't formed a new bond yet. So that energy will be regained once we go to products, but we have to go through this higher energy transition state first. Now, as your temperature increases, the amount of molecules with the required activation energy also increases. So if we look at our thermodynamic range of energy, we can see that as we increase our temperature, more molecules have the activation energy needed, and so reactions speed up as you increase the temperature. Now we can solve the Arrhenius equation to give a linear form. So there, the natural log of the rate constant is that activation energy divided by R, the gas constant, times 1 over the temperature, plus then the natural log of A. So then our equation is in linear form, the y equals mx plus b form. And so if we graph the natural log of k versus 1 over temperature, we should get a straight line, and we can get the slope. If we multiply the slope of the line by our R value, we can get our activation energy in joules. We can also use the y-intercept to solve for A. There's also a 2-point form. If you only have two temperature and rate constant data points, you can use the 2-point form, which will get you an estimation at least of your activation energy, but you won't get your frequency factor, the A, out of it. So let's work through an example. We have a reaction here. It has a rate constant of 2.57 per molar per second at 701 Kelvin and 567 per molar per second at 895 Kelvin. Find the activation energy in kilojoules per mole. So here we're just plugging in values. The natural log, I'm going to define this as 1 and this as 2. So the natural log of 567 over 2.57 is equal to our EA value over our 8.314 joules per mole times Kelvin times 1 over T1 is 701 minus 1 over T2 is 895. So I can work that through and solve for my activation energy. So my natural log thing there works out to 5.396 is equal to EA over 8.314 times 3.092 times 10 to the minus 4th. And I can solve for my EA. And I get an answer of 1.45 times 10 to the 5th joules, because my 8.314 there is in joules, and my moles and my Kelvin cancel out. And so that is 1.45 times 10 to the 2nd kilojoules, or 145 kilojoules per mole. The moles don't cancel out, never mind. Another practice one for you. Again, work it through, pause the video, then you can come back and check. The chirping of tree crickets has sometimes been used to predict temperatures. At 25 degrees Celsius, the rate was 179 chirps per minute. 21.7 degrees Celsius, it was 142 chirps per minute. What is the activation energy of this process? Remember that the natural log of K2 over K1 is equal to EA over R times 1 over T1 minus 1 over T2. So if I work this out, plug in my numbers, my natural log of, so if this is my 1 and this is my 2, natural log of 142 divided by 179 is equal to EA over 8.314 times 1 over T1, 25. This needs to be in Kelvin because of my R. So 1 over 298 minus 1 over 297, 4.7. So then I can solve for my EA, and I get 51,300 joules, which is letter B. That is the correct answer.